Today we are going to perform another optimization tutorial with Nastran Solution 200. This one's very special because we are dealing with the built-up structure. Let's go ahead and talk about this one structure that you see here on the screen. Initially, this is what our our structure looks like. The thickness of this beam cross-section has a value of 0.1 inch. The thickness of this plate is 0.15. The entire weight is 6.96 units of weight. We're going to let both the thickness of the beam cross-section and the thickness of the plate vary, and our goal is to minimize the weight. There are some design constraints I will get to in a moment, but first let me discuss what we will cover. We are going to talk about the optimization problem statement. I'll give you more details on what are we varying, what are we maximizing or minimizing, and what are design constraints. More importantly, I'll show you each step you need to take for Nastran Solution 200. After that, I'll perform the optimization. I'll give you some guidance on how to view the results, and then at the end, we'll optimize the original finite element model with optimized structural dimensions. If you're a professional engineer and would like more advanced training, or if you have a general Nastran Solution 200 question, you can contact me at this email address and I will definitely get back to you with a response. If you are a student or a professional engineer and would like free access to the Nastran Solution 200 web app, you can also send me a request at this email address. This example is from the Nastran Optimization User's Guide. If you want a more thorough explanation of this example, I highly recommend you refer to Chapter 8, subsection Stiffened Plate. Now here is what the finite element model looks like on first glance. It looks like it's just a flat plate with no reinforcement in the form of a beam. When you shrink the size of the elements, you then see these one-dimensional or line elements here. These line elements have a cross-section defined, although not visually shown. And here in this last plot, I'm showing you what the cross-section looks like for those line elements. We have two load cases for this example. All the constraints we define would not be applied to each load case. There will be different combinations of constraints we apply to each load case. This is usually very complicated, but in this web app I'm going to show you, the process is very streamlined. Now let's go ahead and talk about the design variables. So here I'm going to let the thickness, and here it would help if I use a highlighter of some sort. The thickness here, this will be my first design variable, x1. Then the cross section has a thickness here. I will let that be represented by x2. And here we have the respective bounds for both of those design variables. One thing we want to avoid is what I'm calling interference. Remember, the line element is specified in the same plane as the two-dimensional elements. There is an offset property that says from this point, offset the cross-section some amount. If we do not take into account the offset, you can have this scenario where the thickness of the shell elements increases and begins to interfere with the beam cross-section as you see here. We then need to impose another relationship, if you will. I'll call this the offset of the C-bar elements. We're going to say that the offset here, and here it might be worth drawing a line through the cross-section, this offset is defined by half the thickness of the plate. So here we're just going to estimate that to be 1.5. And then, or actually this, this dimension 1 represents the height of the beam cross-section. And we're going to go ahead and divide that by 2. On top of that, we need to express from the midline to the top fiber of this plate, if you will. So that will be defined by half the thickness divided by 2. Here the thickness is represented by design variable x1. So now the offset is in terms of the design variable. So as the thickness of the plate increases, it will drive the offset, so we avoid the situation where we have this so-called interference. Here on the left, I just have a summary of the design variables I just discussed. Now, in terms of your outputs, we still need to define the objective and the constraints. Your finite element model will produce dozens, hundreds of quantities. You might produce a weight response. You might produce displacement, stress results for each load case. And now it's up to you to decide what you want to optimize, what's your objective, and what are your constraints. So here, weight, we'll go ahead and set that as an objective. We want to minimize the weight. And as for stress constraints, we have both beam and planar elements here. So for the beams, what we're going to say is for every element here, and we have 1, 2, 3, and 4 elements. For each element, let's make sure that the endpoints of the elements, endpoint A, and you can't see it here, but it's inside endpoint B. So you can imagine that if we take this element and line it up here, one point would be point A and one point would be point B. We are going to say that the maximum stress should be between negative 25,000 and positive 25,000 here. Here in the top right hand corner, I have a better explanation of what we're doing here. Here we have a bar subjected to a bending moment. This will cause the bending stresses that you see here through the cross section. If we took the maximum of this point, the maximum here would be positive 4.95 megapascals. So here we're saying constrain the maximum and make sure that's never above the limit we are imposing. This is also done for the opposing end of the element. So you can imagine we have a stress distribution here, and we are making sure that the maximum stress is never beyond this range. So again, we're doing this for point A and point B of this element, and we're doing the same for element 2, 3, and 4. Also, the plate, we want to make sure that the von Mises stress for both the top and the bottom here is always within this range. And here I should make a correction. Von Mises stress will always be positive, so there's really no need to specify a lower bound. So here, let's go ahead and make these positive 25,000. And now we will have displacement constraints. We have two load cases. One load case has a point load, and the other load case has a pressure distribution. So that's why we're going to monitor the displacement at two different points, and we are going to have different constraints for these points. So we are going to say that the Z displacement of node 10302 is to be within this range, and then we have a comparable constraint for node 10203. And here, just a reminder that the stress constraints will be assigned to both load cases, but the displacement constraint will be applied to different load cases. And here is just a snapshot of the entire problem statement. And now let's go through the procedure you need to take for Nastran. You will need to first start off with a BDF or DAT file. So here, let me exit the PowerPoint. And let me minimize this. And on the desktop is a DAT file. I've already gone ahead and created the finite element model in the pre-post processor. I've already performed my first static analysis. The model is error-free, and the pre-post processor has exported a BDF or DAT file here. This BDF file then needs to be converted using the Nastran Solution 200 web app. And this web app is available for free if you're an engineer or student. Here's my email address if you would like access. This web app will allow you to take an existing BDF file and convert it to Nastran Solution 200. This is where you specify your variables, your objective, and your constraints. So let's go ahead and go through that process. In the web app, let's go ahead and select that BDF file and upload it to the web app. The first thing the web app will do is identify everything that can be set as a design variable. Here, I know that I want to set the thickness as a design variable. So here, the thickness of P shell 1, I'll set that as a design variable. Let's go ahead and look for D. Here are the dimensions for P bar L1. This first dimension specifying the height of the cross section. Dimension 2 is specifying the thickness of the cross section, and these other parameters are specifying, I believe, the flange dimensions. I cannot recall. But here, let's go ahead and select the plus icon here. And now we've set x1 and x2 as design variables for the thickness and the thickness of the beam cross section. For the bounds, we want to make sure that they are within 0.001 and 10. And here, let me go ahead and copy this over here. And now let's focus on the offset. So here, let me type in W here. And you can see that we have offsets for each element. What I can do here is click on options and click on DVXRel2. I get a new second column here, and let me click on the plus icon here. This moves this property to this table here. This table, I can specify that expression of 1.5 plus x1 divided by 2.0. So now the offset, known as property W3A, will be driven by this expression, which is in terms of x1, which is the thickness of the plate. I can also do the same for the other ones. I can click each plus icon individually and do it like that. Or I can use this table to quickly create the relationship. So here, I'll type in 1.5 divided by 2.0. And then here, when I click create, it will set all that's visible here and create a DVXRel2 relation. So now let's go ahead and look at that result. So here are all of my offsets, and here I have all the equations that govern the offsets. So let me go ahead and look at my notes and make sure everything looks fine. Let's move on to the objective. Here, very simple. Out of all the quantities in your outputs, let's go ahead and just pick the weight and minimize the weight as the objective. Let's move on to the constraints. Let's go ahead and set the stress as a constraint. We want to apply this to any element associated to P bar L1. Or here I get an error saying the PID doesn't exist, and here it should have been 3. And here I want the end A maximum, and the lower and upper will be negative 25,000 and positive 25,000. And here, let's go ahead and make sure we've typed this in properly. So this should be negative 25,000, and this should be positive 25,000 here. Let's go ahead and repeat the process 3 more times. So this would be for P bar L3, and this would be for end A maximum. Let's go ahead and do the same here and here. Now for P shell, let's go ahead and switch this to von Mises stress for the top and bottom fibers. And then we'll go ahead and assign this to P shell 1, and we'll use the same upper bound here. We also need to define 2 displacement constraints. So here, let's click on the plus icon 2 times, and let's go ahead and configure this constraint. This will be in the Z direction for both, and one displacement constraint will be for node 10302, and the second node will be for 010203. And then for the upper and lower bound, we will go ahead and specify negative 0.1 and positive 0.1. And this will be different, 0.03 and 0.03 here. Now let's move on and assign these constraints to the load cases. In Nastran terminology, generally a subcase can be thought of as a load case. The definition of a subcase for Nastran is a little bit longer, but here, just to keep it simple, think of a subcase as a load case. Here, I have all of my constraints laid out for me. I can then specify which subcases get which constraints. Let me first show all the subcases 1 and 2. If I mark this checkbox here, it will automatically include all of these visible constraints and apply them to all the subcases. Hence, you see this gray bar. The gray bar means I'm going to take all of these constraints and I'm going to apply them to subcase 1 and subcase 2. Now, let's suppose we want to make an exception. Here, if I want to go ahead and assign all the constraints to subcase 1, but I want to leave out constraint R6, I can just select all these checkboxes and deselect this one checkbox. The gray bar then becomes a blue bar, indicating that there's an exception. All the subcases, or all of these constraints, are applied to all the subcases except for subcase 1, since you get a new colored bar. For subcase 2, we want to do something similar. For this, we want all the constraints except for R5. And here, since all the other subcases have constraints, there's really no point to having constraints for all subcases. So here, we'll just deselect everything here. So again, subcase 1 is going to get constraint R1, 2, 3, 4, and 5. Subcase 2 is getting R1, 2, 3, 4, and 6. And remember, I discussed this a moment ago, so feel free to go back and look at this. One other thing, as you configure your constraints, at first it might be a little confusing when you're setting this up. As confirmation, you can come back here to subcases and look at the description column. This will give you an idea of the constraints. So here, for example, R3, we have constrained the stress, specifically the von Mises stress for the top fiber of any element associated with P shell 1. R4 is very similar, except this time we're doing it for the bottom or Z2 fiber of the plate. One thing to keep in mind is every element here is associated with P shell 1. So everything except the line elements. So let me shrink that. So every quadrilateral element you see here is associated with P shell 1. We apply the stress constraint to all of these elements. Each element will produce its own von Mises stress value. So here we have actually constrained 16 elements. So although this looks like we have one constraint, we've actually constrained 16 element von Mises stress values. So here R3 again is linked to 16 element stress values. So is R4 and R1. This is associated to 4 element stress values. And the reason is because here I have 1 element and A, 2 element and B, or and A, element 3, element 4, and A. So there are 4 points where I constrain the stress. And here the same for R2. This would be and B. So this has 4 stress element, or rather, has 4 element stress values, 4 element stress values associated, 16 element stress values, 16. Here, I have only one component for one node. So this is corresponding to one constraint value. And so is this one. So now let's zoom out here and go to the exporter. Let me go ahead and make sure I have all my files deleted here. And let me download new versions of this BDF file. Remember, those BDF files have been converted from this initial BDF file to Solution 200. I can start Nastran, take the model BDF, and run to perform the optimization. You have a number of files that are created for you during and after the optimization. After each optimization, open up the F06 file and look inside at the very end. So make sure that towards the end it says run terminated due to hard convergence at an optimum. This is indication that an optimization has been successfully completed, and here I have confidence that everything went well here. Let's go ahead and click on the plotter in the web app. One of the files created during the optimization is a CSV file. You can open this in Excel and create plots of your own, but the web app includes a plotter for you. So what you can do is upload the CSV file and you can look at the results. You can see what the objective change was during each design cycle. Here, I started with the mass of 6.96. I ended off with the mass of 5.47. Let's look at X1. Here, I have the change of design variable X1, which is the thickness of the plate. It started off at the value of 0.15 and it ended at a value of 0.11. The thickness of the beam started at 0.1 and it ended at 0.08. And here you can also look at the normalized constraints. Now let's go ahead and let me make a comment regarding normalized constraints. Here we have 4 beam constraints plus another 4 beam constraints plus 16 shell constraints for von Mises's top fiber plus another 16. That is well over 40 constraints. During each design cycle, 1, 2, possibly 4 of those constraints are dominating the design cycle. For the next design cycle, it might be another different 4 or 5 design constraints that dominate the design cycle process. So here, this could be the stress value in the element that's limiting the model. So it's going to optimize for this one constraint. For the next design cycle, it might be something completely different. It might be the displacement constraint that is dominating, and so on and so on. Here, a negative value means that your design constraints are being satisfied. When you hit a positive value, that means one of your design constraints is being severely violated. And here you can see that the optimizer starts with a very satisfactory design and then becomes violated, and the optimizer works to get this to a value of 0. So a value of 0 for normalized constraint means that you're right on the edge of failure, but you're still satisfying your constraints. If I were to go back here and import my results, perhaps we can find out which value is the governing value. So here, let's go ahead and just import some of the results, and we'll see if I can find out which quantity is the one that's governing. Let's go ahead and results, and let's go ahead and look at the displacement here. And one way you can determine what constraint is governing the design, if you go up here, and let's go ahead and look at that 06 file. Let's go up here until we find the final analysis. This is a summary of the objective, what the final value is. So 5.47 units of mass. The final values for your design variables. And here, if we keep looking, we get this row with the double asterisk. This is the normalized constraint value of 2.4418. And if I go back here, I get 2.4118 e to the 5. So this value is this normalized constraint value. This is corresponding to the stress with label R3. And now you might be asking yourself, which element in particular is the one that is causing this? So let's go ahead and see if we can investigate. Let's trace the 4 down to this next section called responses. So here we get a new section. Here we get stress responses. And here let's look for the internal ID 4. So again, we found this double asterisk here. It's pointing me to label R3, and R3 is this R3. So we know it's associated to one of the von Mises stresses. but we want to know which element in particular is the limiting factor in the optimization. So here we get an internal response ID of 4. So here, think of this as a table, and this is a column. We'll take the 4. We'll go ahead to responses. So here's responses, and we'll trace it to internal ID 4 here. And here you can see that it's R3. So here's the R3. This is the stress value. And here it is. Element 3 is the limiting factor. And it actually has a value of 25,000 units of stress, which coincidentally is the upper bound of the constraint. So again, the optimizer will try and minimize the weight until one of your constraints is violated. Here we found out that element 3, or the von Mises stress of element 3, it's what's limiting the optimization. So here, let's go ahead and plot that. Let me see if I can find the stress value here. Let me turn off element averaging. So here in red, we have a value of 23,000 PSI. And then I think we were looking at the top fiber. Yeah, the top. So let's go ahead and look at what that was. So there we go. So here are the elements in red that have hit the upper bound of the von Mises stress constraint of 25,000 units of stress. One thing to keep in mind here when you look at the results, you have 4 sets of data. This first row is for sub case 1 or load case 1 for D0. If you look back at the plotter, you'll notice that they use D1, D2, D3. This is used to label each design cycle. The initial design is usually known as design cycle 0. Hence, in Patran, we see D0. What about the D5? So here we have D1, D2, D3, 4, and 5, which is known as the final design. So here, this is load case 1 of the initial design. So let's go ahead and look at the von Mises stress state. Here we had 15,000 units of stress. Here, load case 1, final design. You can see the stress went all the way to the upper limit. And here the second set of data. This is for subcase 2. So we can go ahead and plot that and that. I recommend doing this check just to make sure everything looks okay. On one occasion, I slipped up. I made my displacement constraint, or rather, I made my stress constraint 250,000 units of stress, and you should have seen the deformation on this plate. It was really high. So always make this final check just to confirm everything is reasonable. Let me go ahead and minimize all of this. So now that we know that our design constraints are satisfied, we need to update the original BDF file. This BDF file, let's go ahead and look at this. We have old data for the beam cross-section. The beam cross-section originally had a thickness of 0.1. That's outdated. The thickness of the plate had an initial value of 0.15. That is outdated. Let me go ahead and create a copy on my desktop of this BDF file. So this BDF file here is shown on the screen. We need to update these old values of the thickness for the plate and the beam cross-section. In the same folder where you perform your optimization, open the punch file or the PCH file. This file includes updated properties for those parameters that have been modified. So for P bar L, here's the new thickness of the beam cross-section, 0.08386. What I can do is move these side by side. Let me see if I can do this again. I want this on the right. Here we go. So I can move the new entries from the left and paste them on the right. So let me zoom out here and here. Here, what I'll do is I'll copy the P bar L entry, or I'll cut it, and then I'll paste it here on the right. So here, my new updated value of 0.08386. Here, the P shell value is 0.15 for P shell 1. Here's P shell 1 with the new thickness of 0.1127. So let me go ahead and cut this entry and paste it here. So let me go ahead and paste that here. And now, what about these C-bar elements? If you recall the offset that we defined earlier in the video, that is contained in the C-bar elements. So what we can do is cut these C-bar elements, 31, 32, 33, and 34. We can locate the same C-bar elements here and replace those. These ones have old offset information, so we'll go ahead and paste those there. And so here we have the new offsets that we've defined, or that the optimizer has found for us. So now let me go ahead and save this file on the right. And now on my desktop is a new version of that finite element model, but it has the optimized structural dimensions. And that is the last step in this entire tutorial. As always, if you are a professional engineer and you want to start with Nastran Solution 200, if you want more advanced training, please send me an email and I will get back to you with some support. If you are a student or a professional engineer and would like free access to the Nastran Solution 200 web app, my email is here and I would be more than glad to work with you on that. Thank you for watching.